So welcome to the Codex seminar. Speaking today is Chris Manon, and he earned his BS in mathematics at Purdue University, followed by an MA and PhD in mathematics from the University of Maryland. He was then an NSF postdoctoral fellow at Berkeley. Next, he was an assistant, then associate professor at George Mason University before moving to the University of Kentucky, where he is now and currently serves as the director of the University of Kentucky Math Lab. His research areas include algebra of conformal blocks, character varieties and configuration spaces, integral systems, tropical geometry and reductive groups, and tropical geometry and Newton Okhunkov bodies. And he has also attended 2 workshops in frames and geometry. So he's really bringing that geometric power to frame theory. So let's take it away, Chris.
Okay, thank you. Excited to speak in Codex. So everything I'm going to be saying is joint work with Alex Fink and Milena Herring. So all good ideas are theirs and all mistakes are mine. So let me just sort of introduce the things that we're going to think about. So I'm going to start with the space of m by n complex matrices. We want to think of a matrix like in the frame sense. We want to think about it as a collection of column vectors, where each vector is in CM. This bar bracket n thing is going to be the index set of the column vectors. And what's down here on the bottom of this slide is the basic construction of the talk. So we're going to define a map which takes this matrix, turns it into another matrix, and then takes the spectrum of that matrix. So the first step in this map is we're going to apply the frame operator to this m by n matrix. So we're going to take each column vector and multiply it by its conjugate transpose, and then sum all of those up. And this sum is going to be over all of the columns in a specified index set A. And then what we get is an m by m Hermitian matrix. And we're going to take the eigenvalues of that matrix and write them in decreasing order. So that's the map lambda sub A. Take an m by n matrix, make this Hermitian matrix, and then take its spectrum. Okay. That will be the sort of basic construction that we're going to build the construction that we're interested in out of. So the image of this map is notably a polyhedral cone. It's the cone of non-negative real numbers that are decreasing until they hit either the number of things in our index set A plus 1, or M if our index set is bigger than M. Okay. So once again, this map depends on a choice of a selection of indices that specify certain columns. So an example, we could take just a single column vector of length 2 and apply this, and we're going to get a pair, the trace of the corresponding Hermitian matrix, and 0. Okay. And it's notable for this talk that when we do this quite clearly, since we wrote the eigenvalues in decreasing order, we get a polyhedral cone. So the objects we're really interested in this talk are constructed as follows. You pick a set of subsets of this index set. So each of these sets AI is, a selection of columns out of 1 through n. And from such a selection, we can make a map, which I'll call lambda sub S, from the m by n matrices to, Rm to the number of things in S. And this map is just the product map of these spectrum maps over each element in S. Okay, so we're picking a set of sets. And for each set in our selection, we have a spectrum map, and we were interested in studying the image of the product of these spectrum maps applied to the m by n matrices. So each of these spectrum maps is continuous, and so that makes lambda S continuous, and its image is some connected subset of this real vector space. And we want to know, what is it? What does it look like? What kind of geometry does it support? So that's the sort of question we're interested in. So next I'm going to go through a few examples to illustrate some of the objects you get when you apply this map for different selections of S. So the idea is, as we change the subsets we pick, the objects that come out of the construction will change, and the moral of the story is they're usually interesting objects from geometry, integrable systems, representation theory, etc. All those things that Emily listed in my introduction. Okay, so here's an example. Usually for these examples, I'm going to make this a short fat matrix. M will be less than or equal to N. So let's let S be the set that has all the singletons, 1 through N, and the total index set in it. So we're going to take the total frame operator on this matrix as one of our outputs, and then the frame operator applied to each column as our other outputs. And so here I've drawn S as a poset. We've got the singletons all including into the total index set. I'm going to do something a little different from what I said in my preamble here. I'm going to actually fix a spectrum that I want the total frame operator to have. And I'm going to do that because it gives a cool example. So if I insist that the spectrum of the total frame operator is mu, and then I look at the set P sub S of all of the spectra that fit into this set system that come out of this spectrum map, what I get is a polytope that's linearly isomorphic to the Permutahedron on the vector that you get when you start with mu and then you put enough zeros after it that it fills out to N. Okay, and so the Permutahedron is the polytope that you get when you take your favorite vector, in this case, this mu with a bunch of zeros at the end, and you act on it with the symmetric group in all the ways that you can, and then you take the convex hull. So this is one of the types of sets that naturally comes out of this spectrum map construction. And here's a picture of 3 different Permutahedra below. Okay, so that's the first example. And notably, in this example, we get something convex and polyhedral. Okay, so here's a second example, and it's like my personal favorite. If you take the set system, which is all of the initial intervals in the index set, so 1, 1 and 2, 1 and 2 and 3, 1 and 2 and 3 and 4, all the way up to 1 through N. So you're computing all the partial frames and then taking their spectrum. And then you look at all of the outputs of the spectrum data that you get from that. You're going to get the cone of so-called Gelfand-Cetlin patterns, which are also known as Eigensteps. So these are a well-studied object, and they've appeared in the frame literature in various places, in particular by Cahill, Fickus, Nixon, Poteet, and Strawn, and then also Haga and Pagel. This cone is the cone of non-negative real numbers that fitted into a diagram like what I've drawn here, where every time you see a blue arrow, that means that the thing at the foot of the arrow is less than or equal to the thing at the head of the arrow. So the idea here is you've taken each of these frame operators and taken its spectrum and then sort of flipped the order from what I have at the top of the slide, so that the first row of this diagram is the total frame spectrum, the second row is the penultimate frame spectrum, and so on and so forth, all the way down to the first column vector at the very bottom. And then these will fit into these so-called interlacing patterns like I've drawn here. Each successive spectrum will interlace with the next according to the way these arrows work. So Gelfand-Cetlin patterns are math famous. They appear in a lot of different places. In particular, they appear in the study of degenerations of flag varieties. They're a very useful combinatorial gadget in representation theory, which I'll talk about in a second. And they've appeared in the study of funtifs and untifs before. So what I'm going to do next is explain a little bit more of the background of these patterns and use that as sort of a excuse to explore some of the constructions that we might use later when we're interested in more general sets S. So here's a little aside on the representation theory associated to the Gelfand-Zetlin patterns. So the representation theory that comes into this story for our purposes will be the representation theory of the general linear group of M by M matrices. So these are M by M complex matrices with non-zero determinant. So this is what's called a reductive group. And so it's rational finite dimensional representations all decompose in sort of atomic pieces under direct sum into so-called irreducible representations. And the idea is if you know the irreducibles, then you know the whole representation theory. And in this case, the irreducibles have a lot to do with these objects that we get from the spectrum maps. So in particular, if we take a decreasing sequence of non-negative integers, we can think of that as an object from this theory called a Young diagram, which is just a series of boxes that get smaller stacked on top of each other. And so for every Young diagram like this, there's an irreducible representation and vice versa. So in particular, if you just take one row, nothing stacked below it, that corresponds to the irreducible representation that you get when you take the symmetric power of C to the M as a GLM representation D times, where D is the length of the row. So these interlacing patterns come into the representation theory as follows. If you have two of these decreasing non-negative tuples of integers, and they interlace, like in the Gelfand-Zetlin pattern, that corresponds to a very specific relationship among the representations. It means if you take the representation associated to the lower row and tensor it with a certain symmetric power of C to the M, that will contain as a summand the representation in the upper row. And all of this stuff is happening inside the coordinate ring of the M by N matrices. And it bears a lot of resemblance to the geometric picture that we're trying to study with these matrices with a given spectrum. And that's what I'll talk about next. So the Gelfand-Zetlin patterns also encode geometry of orbits in the Hermitian matrices. So I'm going to abuse notation a little bit here. And I'm going to think of a decreasing tuple of non-negative real numbers as also a diagonal matrix. So in particular, a Hermitian matrix. So, to the decreasing sequence D1 through DM, we can make a matrix where that's the numbers going down the diagonal, and that's what I mean. So given such a guy, which is like the potential set of eigenvalues for a Hermitian matrix, we can look at the orbit through that diagonal matrix. In other words, all of the M by M Hermitian matrices that have that tuple as its spectrum, where the orbit is taken under conjugation action by the M by M unitary matrices, which is a nice compact Lie group. So as an example, if we take the diagonal matrix, which is just 1 in the upper corner and 0 elsewhere, if we multiply that by our favorite non-negative real number and take that orbit, we get a space which is homeomorphic to projective space, PM-1. And if we take a more complicated spectrum, we're going to get a so-called flag variety, which are objects of interest in algebraic geometry and symplectic geometry. And in symplectic geometry, these are also known as coadjoint orbits, and they come equipped with a very nice specific symplectic structure that's inherited from a Poisson form on the Hermitian matrices. Okay, so there's some nice geometry here in these orbits, but really what's going on is we're just looking at, diagonalizing matrices. So in this context, when you have an interlacing relationship, like on the previous slide, what it encodes is a containment relation between orbits. So if, mu interlaces lambda, like in the bottom of this slide, what it means is that, for some d that you can compute, the set that you get when you pointwise add the orbit through mu and the orbit through this projective space I mentioned earlier will contain the orbit through the top row, through lambda. And so this is a familiar story. It's in particular studied by Horn. It's the one special case of the Horn problem. And what it says is that given a Hermitian matrix of spectrum lambda, you can decompose it into a sum of Hermitian matrices with spectra of mu and this multiple of 1, 0, 0, 0, 0. Okay, so that's the geometry and the representation theory of these Gelfand-Sutherland patterns. And you'll notice that there's a nice relationship here. We have V lambda including into this tensor product involving mu and d. And here we have O lambda including into this sum of O mu and O d. Okay, so that's the second example. Going way back in time, if we take this particular set of sets and we look at this eigenvalue set, we get a cone that is famous in representation theory and symplectic geometry that encodes the spectral relationship between these frame operators. And so once again, this set ends up being a convex polyhedral cone. So let's look at one more example, or collection of examples. The sort of generalization of the interlacing relationship I mentioned on the previous slide. So this is all under Horn's problem. So if we let our set S be two disjoint index sets, say like 1 through 5 and then 6 through the rest, and then we also throw in their union, we'll get a diagram that looks like this. And the result will be another famous cone in representation theory and the study of spectra of matrices. It will be a subset of the triple product of these delta cones associated to the index sets we're interested in. And what it will be is it will be all lambda associated to A, eta associated to B, and mu associated to A union B, such that O mu is a suborbit of O lambda plus O eta. And it's known that this set is also a polyhedral cone. It's a projection of a cone you get from the Littlewood-Richardson rule, so there's some representation theory coming in. People have used cohomology and other techniques to compute the inequalities that cut out this cone. So in particular, they're known inequalities, which cut this cone out of Rm cubed. And it also has a representation theoretic interpretation. If you look at the integral points in this cone, it's all of these integral points which represent representations, such that if you take a sufficiently high multiple, which is this L here, you get that the mu guy is contained in the tensor product of the lambda and eta guys, mirroring this relationship here, with the condition that you have to take a sufficiently high multiple. And so this is the topic of a few different nice things in representation theory: Berenstein-Zelevinsky triangles, hives, and the work on the saturation conjecture of Knudsen, Tau, and Woodward, which concerns this L that you have to take. And so representation theory can come in and give you the inequalities which cut out this set. And so once again, we get a space for our PS, which is very nice. It's convex and it is, polyhedral. It's the finite intersection of a set of half spaces. So that's 3 examples where, we have these sort of general classes of sets S, where in each case we get polyhedral cones as our piece of S. So we want to know, why is this happening? And does it happen for all systems of subsets S? That's the question. And so what will follow now is a overly complex explanation for why the very first sort of pre-example yielded a polyhedral cone. Once again, that example, it's very easy to see you get a polyhedral cone. This is not in any way a necessary set of techniques to prove this, but this is an excuse to introduce a few techniques and constructions which can help us analyze P sub S from more general systems of sets S. So the space of M by N matrices is really nice. I think we all agree on that. From a symplectic geometer's point of view, it is a Hamiltonian UM space. So UM is this space, is the set of M by M unitary matrices. That's a nice compact Lie group, as I said. And the action on the M by N matrices by UM ends up being one of these Hamiltonian actions. And that means that there is a nice symplectic form on the space of M by N matrices. That form is preserved by the action of UM. And it comes equipped with a map to the Hermitian matrices, which is closely related to this frame operator that came up earlier. And it's called a moment map. So you should think of moment maps in general as the generalization of the equipment you need to prove Noether's theorem, that for every conserved quantity there is a symmetry, and for every symmetry there's a conserved quantity. But for the purposes of this talk, what we're saying is that M by N and its action by the unitary matrices is sufficiently nice that it has this cool map called a moment map, and that moment map for you is the frame operator. And so here's a construction that can be used to analyze one of these moment maps. So if you're given one of these Hamiltonian spaces, so in this case, think of V as the M by N matrices, where this omega here is a symplectic form and this phi is a moment map. You can actually make a new space, which I'll call V naught, called the contraction of V. And what you get when you perform this contraction operation is you get a new Hamiltonian UM space that now has a whole new group of symmetries. In this case, the new symmetries are in action by the maximal torus of UM, and so it's a product of S1s. S1s just being circles. So this is an M-dimensional torus. It's another compact Lie group. So this contraction operation, what it does is it contracts away pieces of the space so that it becomes more symmetric with respect to some circle actions. And you can prove that this contraction map is surjective, continuous, better be. And on a dense open subset, it's actually a symplectomorphism. So it preserves geometric data as well. In particular, the symplectic measure applies on a dense open subset of this V that you get from V naught. And the other nice thing this contraction operation does is it turns the spectrum map into one of these nice moment maps. And so that's what I've indicated with this commutative diagram here. If you go around the upper right corner, this is, you're using a frame operator to get to the Hermitian matrices, and then you're going down with the spectrum map. Then if you go through the lower left-hand corner, you're first contracting and then using the moment map for this new circle action. So one way you can think of this contraction is it does whatever is necessary to turn the spectrum map into a moment map, which it wasn't before. It was continuous, it's nice and all that, but now it's a moment map and we can apply technology from symplectic geometry to analyze its image. So in particular, when we apply this to the M by N matrices, we get this space, the contraction of the M by N matrices along the total spectrum map. And we get that the spectrum map is now effectively a moment map, and we can use a theorem, a classical theorem of Atiyah, which says that momentum mappings of tori are convex polyhedron. And so now we have a overly complicated proof that this set is a polyhedral cone. And this isn't new. you know, it's known that these things should be cones. They're called the Kerr-1 polytope when your space is compact. And this sort of story has been studied with other techniques by Shamar and Bernstein. So the new element here is this contraction space, which is sort of the universal go-between to turn the spectrum mapping, which was already continuous, into one of these really nice moment maps. So the question is, you know, can we make this story, which is true for our sort of pre-example, can we make it work for other sets S? Instead of just being the total index set, can it work in other cases? So in other words, what I'm asking is, you know, is there a contraction map which replaces the m by n matrices with a new space that turns the spectrum map into a moment map, such that, you know, we can achieve our piece of S as a moment image? And so for the Permutahedron case that we first began with, the answer is yes. For the Gelfand-Cetlin case, which is like the most famous and best, the answer is yes. And for the Horn case, this you know, decomposing Hermitian matrices with given spectra, that answer is yes as well. And it will turn out that there's a general class of S sets of sets where this story all works. So a general answer, it's not a necessary condition, but it's a sufficient condition, is that yes, when the set S of subsets is an up tree. So what's an up tree? So S determines a poset of sets where, you know, we draw an arrow between two elements of S when one thing is included in another. So all of the cases we've looked at are up trees. And in general, the idea is you make this poset and you insist that it look like a tree. And moreover, you insist that all of the kind of branches in the tree go up and not down. Okay, so you have like disjoint collections of sets fitted into each other is the idea here. So this is another example of an up tree. You know, we have 1 and 2 including into 1, 2, which includes into 1, 2, 3, and then you can append 3 in there as well. And you can check that, of course, Horn's problem is one of these because it's just 3 things. And, you know, they're going down into the disjoint union. The Gelfand-Cetlin poset, which we drew earlier, is just a chain. And the Permutahedron is sort of the shortest, fattest version of this poset. It's just the singletons included into the total index set. So these are all examples of up trees. So in general, to define this class of S, we're going to say that a set of sets is a full up tree if it's closed under taking intersection and no sort of down shapes appear in the Hasse diagram, in the poset. And we're going to say a general up tree is a subset of a full up tree. And the reason we're going to say that is the following lemma, which is not hard to show. If you have a set S as a subset of another set S prime, and if you know that the eigenset for the bigger set is polyhedral, then that proves that the eigenset for the smaller set is polyhedral as well. And that's because there's a linear projection from one onto the other. And when you linearly project polyhedral cones, you get polyhedral cones. So that's the reason for this part of the definition right here. And so the theorem, first theorem of the talk is that up trees have the whole package. The eigenvalue space is a polyhedral cone, and it's also a continuous moment image of the set of m by n matrices factoring through some mysterious, nice space, the contraction of the m by n matrices along S. Okay, so in other words, this is how you can construct the spectrum mapping. It factors through a moment map. And I want to emphasize here that this contraction space is mysterious. Like there's a machine that says it's there and a recipe for constructing it, but not a lot is known about it. And you know its dimension, and you know that it is a connected thing, but Not a lot is known about its geometry, and they seem like fairly reasonable natural spaces to look at because they're sort of the universal spaces, once again, that make these multi-spectrum maps into moment maps. So in this case, for an up tree, the set P sub S can be realized as a fiber product polyhedral cone of a bunch of horn cones. So in particular, we can explicitly write down P sub S as the intersection of a finite number of half spaces. So kind of all of the nice things happen in this case. So what about other trees? You know, maybe general sets of subsets aren't, it's too much to ask, but what about other trees? So in particular, what if we have a down tree, which is, you know, an up tree turned upside down? So here's a sort of extended example for us. We can just consider taking two index sets and looking at their intersection. So in this case, if we look at sort of either branch of this diagram, it's itself an up tree, even though the union isn't. And so we know that the cones associated to either, the sets rather associated to either branch are polyhedral cones. It's true for PA intersect B and A, and it's true for PA intersect B and B. And so the question is, if we're given a triple, lambda, mu, and eta, where lambda mu is in PA intersect B and A, and lambda eta is in PA intersect B, B, can we find a matrix, can we design a matrix where the A spectrum is mu, the B spectrum is eta, and the A intersect B spectrum is lambda? That's the question. And if we can do that, then we will have proven that, you know, A intersect B, A, B, the guy for this diagram, is a polyhedral cone. So here's a sketch of how to do that. If we start with a matrix M, which sort of realizes the A part, and a matrix N, which realizes the B part, then we can notice that, you know, if we've assumed these matrices are what we want them to be, that is, if their A intersect B spectrum maps agree, then that means that their frame operators land in the same orbit, right? And the nice thing about orbits is that you know how to get around them. And so it's then, you know, straightforward that the frame operator for this first matrix M will be related to the frame operator for the second matrix N by conjugation by some unitary matrix. And so all we got to do is take that unitary matrix and use it on the whole M matrix above. And then just take the columns from the indices that are in A but not in A intersect B and append them to the N matrix. And then that will be a matrix which does the trick that we were looking for. And so the conclusion is that, you know, this diagram, PA intersect B, A, and B, is also a cone. It also gives you a polyhedral cone. And moreover, it is, you know, a fiber product of two cones which are easily computed as projections of the Gelfand-Cetlin patterns. And so with that in mind, we make the following definition. If we say S is a full tree, if it's closed under intersection and its poset is a tree, and we say that S is a tree in quotation marks if it's a subset of a full tree. And the reason I say tree in quotation marks is that not all trees are trees. Here's an example of a non-tree tree. If you take this obviously tree-ish diagram and close it up under intersection, you're forced to put a diamond shape into your poset. And so this is not a subset of a full tree. It's a way of saying that. But regardless, theorem, if S is a tree in quotation marks, then P sub S will still be a polyhedral cone. And moreover, it will be a toric fiber product, or excuse me, it will be a fiber product cone of some known cones, so we can write down inequalities for it. And, you know, all the goodies are there, except we don't know whether or not it's a moment image like up trees are. So this is an open question. We don't know if these cones can be realized as natural moment images of the M by N matrices. So it works for up trees, but not for more general trees, in quotation marks, which aren't as general as trees real. Okay. So finally, what about other systems of subsets that aren't trees? So here is a sort of extended counterexample. If we take this particular set, all the singletons, 1, 2, and 2, 3, and then the total set, 1, 2, 3, 4. You see there's a diamond shape in the post set, so it doesn't fall under the previous two theorems that we just mentioned. And you can do the following to P sub S, where S is this set of sets. You can slice it by setting some of the spectra from the subsets equal to specific things. I won't say what, but you can pick them out. And you can project it linearly in a certain way, which I also won't say how. It's related to taking the traceless part of a Hermitian matrix, though. But the point is these are operations that preserve polyhedrality. If P sub S were a polyhedral cone, then slicing it would keep it polyhedral, and projecting it would keep it polyhedral. But when you do this, you get the set of pairs such that the sum of the squares is less than or equal to 4. And that is a quarter of a circle and is most definitely not polyhedral. It's still convex. It's not a polyhedral cone. So that proves rather that P sub S is not a polyhedral cone. In particular, this set is inspired by some geometry of n-gons in real space stuff. You can realize this red and blue quantity as the cross diagonals of 4-gons in R3. So this is actually sort of an incomplete counterexample, though, because you can go way further. So if we take two incomparable sets and throw them in our set S, incomparable meaning neither is contained in the other, and if our set S contains something above both of them and below both of them in the post set, then it won't even be a convex set. And the way this can be proved is that by this trick of projection onto subsets, P sub S in this case will project onto the eigenvalue space of this diamond here, and it can be shown directly that these are not convex using some tricks about orthogonality. So in conclusion, we can answer the question, is P sub S a polyhedral cone whenever S is full, that is closed under intersection. And for some other S, when you can use these projection relations, but for general S, we don't have an answer. And another question I want to finish with is, I think these spaces M sub S, like I said before, are interesting. They're quite natural from the geometric standpoint as being the closest space to the M by N matrices that makes these multi-spectrum maps for up trees into momentum mappings. And so the question is, what are these spaces? We know what their dimension is, it's M times N. And we know that they carry the structure of a stratified symplectic space and an affine algebraic variety. In particular, it's a reduced and irreducible variety. So we have kind of a very nice thing to look at here, and it should be cut out by some equations. But its construction is rather abstract. And so we don't have equations for these guys. And I think it would be interesting to find some. And so I guess I will be finishing a little early. Thank you for listening.